So one of the last points that we discussed was the rate at which the data requirements and the data scale operations is increasing, right? I showed you this one from 2016, and then I had another one on the other set of slides. I will convert those over, but if you want to look at the slides again, the ones that I showed in class on Tuesday, those are integrated, embedded within the Panopto, so you can see those there as well. I am trying to record these. I don't know if this one's going to record. Hopefully it will, but it said something about video device input availability, but it seemed like it was still showing that it was collecting it, so we'll see what happens. But one of the key items here is that there are two measurements of the complexity, the relative complexity of many of our machine learning models. One of them is the number of free parameters inside that model, all right? And that's one of the mechanisms that we utilize to say how complex a network is the number of nodes effectively within the system. The second is the amount of data that that model was trained with, right? So that would be its informational density characteristics. So we would say that the larger the model, the more data that the model was trained with, the more informed it becomes about the characteristics of the data set that it's working with. What are some of the limitations and restrictions at the upper end of that system? Well, one of the problems is complexity and the computational frameworks, right? So many of you know that we're becoming more and more reliant on more and more advanced hardware in order to run many of the models we're working with now. And one of the limits, or the upper cap of that limit, is Moore's law, right? Which states that relative to the number of transistors incorporated per unit area of the chip, there will be approximately a doubling every 24 months, right? There's another law that's associated with it also indicates that every 36 months, the relative cost per unit density of the transistor will reduce by approximately half. We've kept this intact, right, structurally, in the indication that as we started off with some of these original systems that were at the 8,000 nanometer range, right, all the way down to the 16 nanometer range with the recent A10 series chips, I have actually seen a fab that may be coming online soon in Taiwan, which incorporates a 3.2 nanometer architecture, all right? The gate density of that is thought to be below what was considered quantum interference perspectives less than 5 years ago. We did not think we would go below 4 nanometer, right? 4 nanometer felt like the absolute bottom, but now we've gotten deeper, right? 3.2 nanometer becoming significantly possible to the point to where we're actually thinking about, they're actually talking about having a large scale fab. Why is it harder and harder to put this stuff on a chip? Well, because if you make one tiny mistake, right, one set of process variability in the lithography of transferring this to the actual chip system. The other consideration is that when you're dealing with structures that are that small, the wavelengths of light are not quite small enough in order to actually create that channel, right? They're bigger than this by orders of magnitude. So we actually have to interact wavelengths of light with one another and look at the side effects of how those wavelengths of light interact with each other in order to etch the chip to be able to make the elements in that chip that small. So crazy, crazy physics is driving some of the things that are creating smaller and smaller chips. I will still say that relative to the functional density and complexity, right, 100 million transistor systems can operate in that 16 nanometer RPFC package at about 30 millimeters, right? The cortical density of the human brain is approximately, well, I think they've said now it's 24 to 27 billion cells. It really kind of depends on what we're describing here, right? So we're talking about a child to an adult. A child, roughly 11 billion to 12.5 billion cells, to something like 27 to 30 billion cells in an adult, right? 30 billion individual components. Those are not transistors. Those are full compute units. Each neuron is capable of doing things that require multiple transistors. So the human brain's structural density and power requirements are still far in excess of anything that we can replicate in silicon. Right? We hoped several years ago that this process would ultimately create things that were very brain-like, somewhere in the neighborhood of, I don't know, the mid-2010s, right? But this graph has been further pushed right as the extension starts off, that some of our original work starting back in the 1900s or pre-1900 with the analytical engine by Babbage, right, mechanical computing, became digital computing by the 60s, became home-scale digital computing by the 80s, and then by the 2020s right now, what are we looking at, right? We know where some of that technology has gone between those localizations. So 2024, we're in here. We should be coming up close on what was originally intended, that the brain power or the compute power capacity of a computing cluster could reasonably simulate the computational complexity of the average rat cortex, right? We can simulate all of the individual neuron interactions of the rat brain. Can we do this?
No.
Not yet. Not yet. This didn't work. This is not quite working out, okay? This graph is flattening rather than going up, all right? So it's not the exponential graph that was expected previously. Moore's law is failing even though we're getting more and more dense systems. Partially it has to do with how much we realize the complexity of those rat brains, right? So even in the neighborhood of something like 10 to 100 million cortical elements in something low order like a Drosophila, which is a fruit fly, right? We just got to the point last year where a reasonable model of an adult fruit fly Drosophila was able to be replicated in a silica chain system. So every single neuron was mapped, effectively mapped from the gene sequence map that makes up one specific type of that fly that is utilized in experiments. So we've just got to the point where we can replicate flies. All right, are they hooked up to anything? Are they doing anything useful? No, not really, not yet. We're just replicating, all right? So when we start making them do something useful is going to be the next rational step of this development. When we start making systems and robots that are capable of the same level of cognitive and memory sophistication as rats, then I think we'll have achieved something, all right? But we're still not there. So if you ever think about all the things that have been done, right, it's all done. I see nothing to do in the world except for just be a technician and work on the stuff, not even remotely. Tons and tons of development is still out there. We're years and years and years away from what was originally intended. But they thought that by 2023, right, what does that say up there? 2023, we will be able to surpass human brain power.
No, definitely. Oh my God.
Even to get up to the number of relative compute units, compute density characteristics of the human brain. And this is not based upon transit performance characteristics, right? This is not about interconnectivity. Anybody understand, everybody ever heard of the concept of fan out? Right? You have one component in an electronic circuit and then you have other components hooked up to it. You've got little gates and channels that hook up to those components. The more stuff you have connected in the fan out, the more power it takes in order to be able to activate all of those things efficiently, right? To distribute that power to the system. The solution to this problem is not the cloud. The solution to the problem is not to add more GPUs to the cluster. Getting wider and adding more things to a data center does not solve the transit time problem. Okay? Understand that after a certain point of width in many of these systems, you can add GPUs up to a certain point to parallelize it, and then what happens? It actually takes more time, if I add more GPUs on, it takes more time to copy the internal elements to those GPUs than you get back in parallelization increase in performance. So even though we can have a data center that has more compute units in it and more functional memory operators than the 11 to 30 billion units we have in our cortex of our brain, they still cannot operate anywhere near as computationally efficiently as a human can in general task performance, all right? Can they do certain things better than us? Absolutely. That's a key factor. Those are the kind of systems we're actually going to look at constructing in this class space, is that we're going to be looking at building relatively sophisticated structures that can replicate many of the capacities of human-like intelligence or human-like capacity to process information and create some decent structural weak AI, all right? Weak AI means that it doesn't matter how it thinks, it's not human-like in its core intelligence, right? It doesn't have to process things that it can explain to us, but it executes a relatively complex task that is not able to be done by any other methodology. Once again, I'm repeating that construct that when you've tried everything else, then try deep learning, okay? Don't start off with it, because if you start off with it, yes, it will be able to do it, but is it also potentially a massive overkill, right? Using a nuke to swat a mosquito, everything that in that space is just a little bit overkill in some of these respects, all right? So as many of these models, I find people going and like saying, hey, we're gonna create a business application. What we're gonna do is we're gonna train it off of this 6 billion parameter model, right? And we're gonna create a chatbot for your business. And it's like, really? You know, you're gonna create a chatbot for a business, right? It has one scope, very limited possibilities and outputs, but you're gonna train it on this GPT model. It's trained literally on every piece of information ever, right? And you're gonna go that should be fine. That's a reasonable amount of computing power to allocate to it. What happens in that case? Businesses begin to get dependent on the workflow operations of having these mechanical systems that replace human interaction. Even companies like Amazon, all right? We're talking about companies that have like borderline more money than God, okay? They can build whatever the hell they want, and they still can't get these things to operate as efficiently. Try to talk to Amazon's chatbot about returning something to Amazon, okay? It's dumb as a rock when it comes to certain things. It's interesting that these companies that really lead the way in these computational and information intelligence systems can't get on that same level, but why? Because it costs so much electric power and compute time power to run the bots that are the very high sophisticated bots like ChatGPT that OpenAI almost went broke trying to figure out how to get its company off the ground, right? By making it free and available to everybody, yes, they got a lot of training data, but at the same time, they open themselves up to a lot of liability. So I want to once again reaffirm to you guys that there is a link between the complexity of the model and the model's quality and utility, right? You can't necessarily always say the more complex model is better. In most cases, we're going to simply use that process of parsimony. We're going to make the statement that the model that accomplishes the exact required task with as few possible parameterizations, the least sophisticated model, is the one that will always be the best selection, all right? That's a modification of a principle that I talk about in one of my other classes, that's Occam's razor, right? All other things being equal, the solution that requires the least number of assumptions must be the solution that is the most viable, right? That's a little bit of a translation. But what am I talking about when I mention assumptions? Okay, we're going to talk about next here the idea of classification. And I say that the most primitive operation of any system, right, any intelligent system, is in fact classification. To be able to tell the difference between two things is the most primitive form of what we would consider something to be intelligent. Why did I say that? Why are could most tasks be reduced down to kind of binary type classifications? Just give me the moment to think about it.
Most decisions usually fit under that. Do this or don't do this.
You either act or you don't act, right?
Yes.
So in the end, if action is the product of intelligence, and I think we would have to make the argument that in order for something to be intelligent, it must do something with the knowledge it possesses, right?
Yeah. So
the argument would then be that all things boil down to do or don't do, right? There is no try. Good. So this is a relationship of a operational classification. First and foremost, notice that I have a region that is being subdivided between two groupings, all right? High-risk groupings and low-risk groupings. So if I wanted to look at this for something like an insurer or maybe a lender, the individuals that rank within the low-risk grouping, right, that have both high savings and high income, right, might be consumers that would be good targets for us to indicate a loan to, right, or extend insurance to, or something like that. Their pattern of past behavior qualitates them, right, makes them appear to be a better customer for our product, or at least reduces the amount of risk we might have in getting them to pay back the loan once we extend it to them. Now, what's the relationship here as it's saying? It's saying if I have a reasonable amount of income, right, but I don't save any of it, that means I'm spending all the money I'm making. Anybody ever notice that people that make more money don't necessarily have more cash in their pocket? Okay? Because you live up to your standard of means. Whatever you make, you're going to spend. Usually, the harder you work, the more harder you play, right? The better thing you buy. You make $250,000 a year, you're going to go buy that new Mercedes, right? I deserve it. At least that's what the advertising is telling me. So I'm going to go and purchase that product. I'm going to think that I'm doing it to reward myself. But that pattern of behavior doesn't necessarily tell you that I am a stable decision maker. So where does the line that exists between these two groups occur? It doesn't follow up with any specific example, right? It's not right on top of the number of individuals that are considered to be the good borrower option, right? Because what would we want to do? We want to actually maximize the number of customers that seem reasonable for us to loan to, right? You don't want to have fewer customers because you don't want to make it to where everybody has to make, and have this exact amount of savings in a specific threshold, right? The reason why I say I want to maximize is I want to kind of put it right in between the support information I have. I have a few examples over here on the low income, relatively high savings that still indicate relatively high risk, right? Because what happens if their job falls through? The savings is going to plummet, right? Because they're not going to be making this moderate income anymore. You have the people that have the higher income but the lower savings. Once again, ultimately, any of the you have something come up, right? Got to fix your car, got to replace the roof, right? Those things pull out of that savings right now, and all of a sudden, all this free income, this free flow of data was no longer applicable. But notice, I don't set it right on top. I don't set the boundary of what I would consider to be a good or bad candidate right on top of any of the given examples. I'm going to place it somewhere in between that information to allow myself the operability to be able to adjust for potential future information. Okay? What is the likelihood that any given individual that falls in this space here, right, is likely going to be a good risk, right? A low risk operation. Probably higher, right? There's going to be a chance that it's going to be low risk than somebody that's further down here. Okay? So where we set the discriminant, where we set the boundary between the elements is tied specifically in minimization of a loss function. So why do I utilize this concept of a loan? Because loans link well to that notion of a loss function. If I give somebody who is a poor risk, a high risk, a loan, and they don't pay it back, what happened? I lost money, okay? So we say that we want to minimize loss. At the same time, that's kind of the inverse structural operation that creates the maximization of gain. So creating this relationship between high risk and low risk customers is a mechanism of classification which is going to come from or be characterized within many, many spaces, right? Being able to tell one character apart from one another, right? Telling one speech phoneme apart from another speech phoneme, right? I draw boundaries around the sounds that make up certain words, and then by identifying them and separating them from the similar sounds in the adjacent space, I create a better understanding of it. So I break up something that seems relatively continuous, like the sounds we make as humans, into little clusters, little groups. And between each one is a certain cutoff point, right? It says, you're no longer the sound, you're the sound, right? Cutting off between those two phonemes. Medical diagnosis, once again, we said this is very common. Well, how do we utilize this? Do you have a disease or not? A cell is diseased or not, okay? Biometrics, facial recognition, pose lighting detection, occlusion, all this stuff is very important to the use of the technology. That's very similar to like when you hold your phone up to your face and it unlocks it. How's that work? Well, it's going to tell you apart from every other human in the world, right? So the computer can reasonably well tell where your face is, and reasonably tell that it is a face, right? But what makes your face different than another face? So the collection of individual decisions that create the separation of you, one, versus the rest of everyone else in the world, is a very complicated process decided on multiple dimensions using a classification methodology. Right? Outlier and novelty detection involve things like detecting faults, but also stuff like maybe fraudulent claims or fraudulent transactions in a system. Right? We want to detect what things are normal and what things aren't normal. Any of you interested in cybersecurity stuff? Right? So cybersecurity is kind of a thing. Okay? Anybody in cybersecurity classes? Okay, a couple of you. One of the things that's interesting about classification and detection with regard to cybersecurity options and systems is we may be able to actually create patterns of behavior to where if a user space is logged into a computer system and all of a sudden they heavily deviate from what we expect from them and they start doing things differently than they have previously, then what's going to happen? We're gonna warrant a security audit. We're gonna say, hey, let's check and make sure this person is doing what they should be doing, right? Let's make sure that we don't have a rat in the system, right? Like a remote access Trojan or some sort of integrated invasive operation system, right? How many people have heard like that terminology before? How many people have heard of rats? Okay, so there are a few people that are interested in some of the cybersecurity stuff. Not as much up here apparently, right? But I try to appeal to everybody. Okay, so anomaly detection, fault detection doesn't just extend to specific events or specific operations, but guess what? It can extend to patterns of behavior. How you type on a keyboard, all right? The pattern by which you hit those keys, the delay and latency between that is uniquely identifiable to you. It is as unique as your walk cycle, right? How your legs move whenever you're walking across the space is a pre-trained neural network oriented in the back of your brain, right? There's a chunk of neural tissue in the back of your brain that orients and organizes motor muscle memory movements, right? Those are hardwired structures. So those are able to be recognized by what you put out. Effectively, one network and its output of that network can be recognized by another network as long as you have enough information about its previous behavior. Okay, whether it's a biological network or whether it's a synthetic network, one way or another. All right. Regression is the fundamental operation by which we're going to analogize the neuron to a loss minimization process. What do I mean by loss minimization when it comes to regression? What would be considered a loss within a regression space?
Downtrend. Would be like a downtrend in your overall regression line?
No. Go for it.
Would it be the error rate? Like from the
Okay.
how much deviates?
So what do I mean by error rate? What is an error when it comes to a linear regression? I just want to see where everybody's at. Okay. Yes.
When there's no, when there's a lack of like
The slope.
a linear relationship between two features, I'm guessing.
That's correlation.
How
Okay.
far?
That's good. That's correlation. How far apart any given point is, I know what you're going to say. I knew you were holding back on it. Okay. How far apart any given point on the line, right, which is the generalization of the pattern that is originating this particular distribution. What is causing these points to exist on this line? Well, some change in mileage versus some change in price, right?
Yes.
Notice what happens. As the price goes up, what happens to the mileage? The mileage also goes up. The more expensive your car is, probably the better designed that engine is, the better mileage or the miles per gallon you get, right? So the cheaper the car is, the more you're going to be paying for it in gas mileage, right? So you saved money on the car, but you're getting less total gas mileage, right? least that's the philosophy. Now, not every system follows it perfectly. Notice, there is a generalized trend within there, but there are a few vehicles that tend to not be directly on that line, right? So this one gets better, has a higher relative price per mileage consideration, right? And the increased mileage considerations there so the increased mileage considerations here relative to price output, right? What do we notice happening? There are points on this regression line, and there are points that are not on the regression line. Matter of fact, more of the points are not on the line than are on the line. Why would that work? Well, because process variability creates these vehicles, okay? How we decide to build the car influences the relationship between the cost of the vehicle and the total amount of gas mileage that it gets, its efficiency, all right? So I would say that not everybody is going to approach the process of creating an efficient engine in exactly the same way. So the relative cost per unit efficiency of the vehicle would be what? Not symmetrical in every case, but generally follow a trend, okay? Regressions are trends. They are common features of groups of data or groups of performative individuals making changes to that system. So why would I want one rule that didn't necessarily satisfy any given individual in the system? Well, I would want to err on the side of caution such that as much of the total distance, right, the aggregate total distance of any given point from this line, summed across all of the points given in the data set, would be put to a minimum. So the function which we create this with utilizes the operational consideration first for the output price y being equal to g of x. G becomes what? A model with fixed parameterization. What are the parameters of this model?
Mileage.
Price.
I would say mileage.
No,
Parameters,
parameters.
not features. You go into features, parameters. Slope. It's got one slope, all right? It's one free parameter.
Oh, okay.
Okay?
I
One parameter.
told the
You know,
slope.
you fell for it. Okay?
Yeah,
You guys fell for it. Okay.
I
No,
fell-
you're right. You're correct. It's like it's easy to sort of fall for what's the difference between these things. Parameter is the thing I can adjust. It's part of the model. Features are the elements that make up the data points that I'm looking for.
Okay.
All right. So a feature modifies is modified by a parameter to create the model. So in this case, we have fixed characteristic, which could be rewritten here as g of that theta, right? Theta times x. In this particular case, other term we use for it is beta. Oftentimes we use beta as a coefficient. So g of x, or g, would be integrated with a model of whatever degree of complexity the underlying system has. So we have one feature predicting another feature. So we have one parameter that we use to adjust the relative slope of the relationship between those two systems such that we minimize the total loss, right? That is the cost of placing a point at some Euclidean distance, right, square distance away from whatever g of x predicts that the value should be at the current value evaluated at x. Everybody with me so far? Everybody done this to some point? Anybody not done this? Good, awesome. We can go a lot faster. Okay. What are the applications of regression? Data set applies to some underlying model system. Model system tells us that from a priori, the past information, gives us or tells us about what is to come a posteriori, or what is in front. Principally, this is related to probability theorem with respect to Bayes' theorem, all right? A most simple version of Bayes' theorem is a linear regression that correlates the input and the output, the dependent and the independent elements of a variable system. So, all operations within a neural network are effectively linear regressions. crazy, right? Huh? Well, what if I told you circles aren't round? What is round? Circles are made up of points.
That's
Okay?
true.
We arbitrarily linked those points together and described the concept of round. What's in between those points? More points. Okay? What's in between those? Lines. Okay? When we give up and we stop making more points, the end is a continuation between the point you left and the point you went into, right? So ultimately, if you zoom in far enough on a circle, what happens? It becomes a series of points with
It's a
little
series of
lines
points.
connecting the outside of it.
Yeah.
Even the most complex curve in the world can be modeled using linear systems. That's what we're going to do, okay? Everything about what we're going to do with fully connected networks is about linking together multiple different lines and saying which line is appropriate per unit space to describe something like a complex curvature, okay? This line, this line, this line, this line, it's effectively the local tangent of that linear operation per that unit is what's active in that region. So the neural network is going to be a consolidation of each of those linear operators coming together. So the response surface that's created for something like a control functionality, the integration operation for being able to tell something like an ARM control using a model of data-driven model for inverse kinematics, all those things can be modeled structurally using neural networks. Now, are these always the best tool? No. But sometimes, weirdly enough, they can be higher efficiency than the closed form solutions. We're learning that. Sometimes reinforcement learning can actually come up with solutions that run faster or forward runtime faster using parallelization than can be done using traditional feed-forward algorithmic methodology. The other consideration is that how accurate do you need it to be? So if the controllers of this ARM can only control down to half a degree of certainty or half a degree of repeatability, you don't need a system that creates more accuracy than that half a degree, right? Because the control isn't present. So you're only going to need to design the system to provide outputs approximated to or close enough to the degree of operable repeatability of something like a robot controller, okay? That's the reason why process variability and the closed form solution, why you can create an approximation, right? You can create an approximation that's almost as good. Once again, probability and computational theorem, I say that the average computer scientist is distinguished from the physicist and the mathematician by the fact that we will accept a generalization, right, or an inference that's way further away from the actual reality, right? It would cause the mathematician to have an aneurysm, right? They go, that's not right, it's not exact, okay? It's like, nobody cares, all right, because the world is not exact. So if we want to concern ourselves with things that are close enough, that's the reason why I say that neural network modeling is often a really good solution, because it can get close enough. Especially whenever things get really fuzzy later on, those close enough systems begin to operate structurally, all right? I'm going to go to my other slides, and we're going to talk about the structural characteristics of neural networks and what they look like. Now, the most primitive model networks operate via a process that was originally developed by an experimental psychologist by the name of Hebe. Hebe hypothesized, based upon a set of, I guess you'd say, informal structural understandings that had been passed down by various biologists and psychologists, cognitive psychologists, about the fact that the neuron was the fundamental computational element of the human brain, right? And he said that if things fire together, meaning that one neuron is activated, right, it detects something, its threshold is engaged, that they wire together, meaning that their connectivity becomes increased, right? There is what's called entrainment. So adjacency and then connectivity implies this notion of patterning. You see there up at the top neurons that become adjacent together, right, or adjacent with one another with respect to a specific sample, indicating that each of those effective surface areas, right, being pushed on, or that weight is detected on a specific area, right, a field, a receptive field, okay? Each one of those is indicating a value at a specific receptive field for the input vector. So let's imagine the input vector first and foremost. What am I talking about? Well, up there we have a system of individual neurons. Those are our input layer. That's the first set of material we're getting from the continuous natural world. Now, how we got that data really doesn't matter. Whether it's a cell, right, that senses pressure on your body in a neurological network, or whether it is a feature vector, right, of measurements, where you got your tool out and you measured across the table and measured across the table, measured height, right? Maybe this is just a collection of values, each individual location representing a discrete field within the object's description. So let me go ahead and pull this up for you really quickly for you guys that are programmers, right? Everybody in here is a programmer at some level. What do we look at when we think about the idea of an object-oriented language? An object becomes what? It is a generalized description of a class of certain type of things. So, imagine tables, right? Table as a class has what? Width, length, height,
and height.
number of legs, right? What color it is, whether it's adjustable, okay? Whether or not it's got a wood top surface or whether it's got a, you know, material construction, right? Those become properties. Those properties are features. Effectively, a single object, when pulled from memory, would look like this to the system what? An ordered set of individual measurements corresponding to the original and enumerated properties of the cells that they were a member of. So we have an object class. The object class, how many instances can we have of it? However many we want, right? How many total fields does it have? They all have the same number, right? The template generates that. The constructor generates the template. Template inherits to the objects. Each object is its own unique table. A data set is constructed of many tables. A table of tables, sorry. All right, so it is going to be an array of components vectorized with each row, right, or column, depending on how the data is oriented, with each row indicating the unique values of the unique positions of each of those measurements containing that specific element. So if what I'm looking up there, each one of those cases is an activation for neurons that are being shown different objects. So each time that changes, that is a different object or a different vector that is being shown to the model.
Okay.
The model will then activate, right? It will say the value of this measurement is at least what is required for me to say, I found it. I saw the thing I was interested in, right? When the neuron activates, effectively, it's standing up and raising its hand, okay? For spiking networks, that means that they are just fully activated, okay? They output a signal. I am on. For other types of networks, we're going to have a degree of activation, right? We can have a continuous operation. We're going to describe the relationship of that activation function and what the activation function looks like. How much and to what degree the neuron is activated can be changed. So interestingly enough, while we can't change the type of activation of the neuron, which theoretically may be possible in biological neurons, maybe they actually don't have exactly the same types of activations in all cases, because they tend to put out slightly different patterns of neurotransmitters when activated by different stimuli, okay? So effectively, it's a similar process which we've modeled, which we've said that the neuron becomes activated, all right? So at the moment, let's just imagine it's fully on, it's fully activated. It has gone beyond the threshold and turned on. Sigmoidal operation does this. past the 50%, wherever the sigmoid is set, right? The logistic function, for those of you who don't know that terminology, is sigmoid, right? Everybody know the logistic function? E, the exponential function, right? The idea would be then that the threshold of operation, right, is going to be when the thing decides to activate. So anything below the threshold, it doesn't turn on. Anything above the threshold, it does turn on. So when I say activation and grouping, or fire together, wire together, notice the wiring below this, the way in which those elements are connected to one another, and the way in which that connection attaches to these neurons at the bottom of the structure is based upon what? Certain patterns or certain items being above a certain value and being detected together. So this set of features, right, table above this height that is adjustable, greater than this width, that has a wood top. Guess what? That's this type of table, right? Table of this height, this width, this color, that isn't adjustable, becomes this type of table. And each one gets a category at the bottom. Each category is effectively the aggregator for saying, hey, this is the place where it stops. This is where it becomes identified as the target of interest. ANNs look like this, all right? So for those of you who are victims of my ISO class, I apologize, okay? I don't know, victim is the right terminology. It felt right at the moment. We have a series of input vectors, all right? What have we done to the network? We took the previous one and we turned it over on its side. Okay, why did we do that? I don't know, whatever, it doesn't matter. Honestly, I think it's because of the fact that we read left to right, okay? So that left to right ideal becomes a workflow. We're thinking about this as this is the input and this is the output, right? Funny enough, this is a bit like the sort of reverse Polish notation characteristics that we often do with equation modeling, right? So we say the relationship of y equals mx plus b. Why do we put y on the left-hand side? Why is the output over there on the left? I don't know. But interestingly enough, programming languages took that same model. Programming language, the output of the function is on the left. So one of the things that made me a better programmer was studying Arabic briefly, right? Because I was forced to think from right to left. So when you're evaluating a network, don't lose your concepts of what's left, right, up, down, okay? Always look at the flow of direction. It will typically follow this pattern of left to right or top down. So on the left-hand side, we have our input feature vector. Notice how it's noted, x sub n, all right? X sub n indicates the value of the feature of some individual sample x. Now, x will have a sample number associated with it, and it could be a member of either the whole data set or a member of a subset of that data set, a power set called a batch. Batch groups are often utilized to overcome some problems that we'll talk about in the future of the network, but that typical input feature space is the feature vector input. Weights, notice that input features directly tie into the weights. The weights are the degree to which that particular feature matters to the next element of the process, which is a summer. Notice that operation is written as a sigmoid, right? Because it's an additive operation. So we're going to take the product of a vector of inputs times a vector of weights, and then we're going to sum together the output of that column, right? So we have this is product, right? The output of the product is here, and at the bottom of that, we're going to have a sum of all of the elements coming into that particular set of vector multiplication. The next element is going to be to determine whether or not the value of that summation meets the requirement as described earlier in order to activate the neuron. Does the neuron respond to the weights of those, to the values of the multiplication between the inputs and the weights? Right? When does it activate? When is it determined to turn on? Notice here, if this is the value across the independent variable, right? And the operational output is either the low or the high level, bit perspective, right? It stays low until the value of the integration reaches this threshold and then does what? Jumps up to the high activation and then maintains. that is the Heaviside step function, all right? The standard step function, which is a maximally integrated natural exponential, okay? It is a sigmoid function taken to its logical extremes. Step functions are operations, all right? They don't really exist in the natural world. There is no such thing as a smooth, perfect step function, right? Nothing moves, current doesn't move perfectly, objects don't move perfectly, inertia stops step functions from actually existing. So why do I say that? Because if we're attempting to model the real world, a step function is probably an overgeneralization. It's too mathy. It's too mathy. So we need what? We need smooth activations that show what? Smooth transitions between states and operations. Two clusters of information, right? High risk versus low risk individuals. How do I separate them if they have some points where they might overlap one another? What happens if a few people that were in the low risk category were actually maybe below the line that I selected? Why might that happen? Remember, once again, the regression function has to optimize based upon loss minimization. So it might choose to throw a few of the samples that it learned the low risk operational understanding from in order to be able to satisfy minimizing the total loss of distance of any given points from that activation function. This step function right here is actually that boundary, right? That is that boundary. It is a decision boundary in the effect of saying that the moment that I cross over from low risk, right, to high risk, what happens? Low, high, okay? It's a hard boundary. Hard boundary. There's no fuzziness, okay? Now, can networks be made fuzzy? Absolutely, right? But we're not going to discuss those in high detail. Structurally, elementally, argument would be given that a neuron map can be written as some function f or a value rk, being r for neuron mapping. The output of any given layer system can be operably written as z, all right? So z would be the value of the activation of the output of that neuron. So if z is the activation function, all right, or excuse me, z is the input for the activation function, not output. Z is the input for the activation function, all right? It's the summation. The activation function then works on z, okay? So z becomes the input for sigma in this case. So I said sigmoid, that's that smooth natural exponential, okay? The value z becomes the input for that second function. It is now a mapping function. So we have mapped the value of the inputs times the weights. What do I mean by weights? Significance. Significance, right? Some features are more significant than others. Some features will be better at helping decide between two groups. So if one feature seems to be really strong at helping make that decision, then that feature will have a higher weight relative to that integration. So the higher the weight, the more significant that feature becomes the decision-making paradigm. If we were thinking about it from the perspective of the loans, once again, it is the income of the individual, right? Or is it the amount of savings that they have that is most highly correlated with that decision, whether they are a good or a bad risk, right? A high or low risk. Whichever of those two factors, relative to the scale of the numbers that are being utilized, will be the element that has the highest degree of significance within the decision-making space, right? How significant is that feature to the decision process? Inputs A, right, become the space input, right? So these are generic. What have I done here? We said X previously, but I also said that I didn't care where X came from. Meaning that the input to any neuron could be the output of another neuron, right? That each individual input could in fact be the summated and activated output of a previous element. So to generalize this, we're going to take it up a scale. We're going to actually create the sort of the loop of process here. Notice if A is the output of the activation of the summation of the inputs times the weights of the previous layer neuron, then in general, the inputs to any neuron are A. Okay? Notice the way this is written is that A1 through AK, right, these are the features, and W1 through WK, these are the weights. Remember what I said previously that coefficients were the linear regression elements in play. Weights are coefficients as well because they determine or designate the relative slope of the regression of the value of that input correlated to the target output. Now, we're talking almost exclusively right now about the idea of supervised learning. So our A inputs, right, W weights, multiplication, summation. And then a term is added to the bottom of this process called a biasing term. What does this help fix? Well, it's relatively straightforward because not every cluster of data is perfectly centered around the origin of a particular space, right?
Yep.
The biasing term helps adjust the offset of the center of the distribution of a specific set of data, similarly to the way in which we say it is the y offset of a slope-intercept formula, right? mx plus b. So this is the b, this is the bias term that applies to be able to adjust for the fact that the inputs and the weights don't understand where each individual point is with respect to the center of the cluster of the data points. So effectively we're going to treat the slope of the line as if the data points are centered around 0, and the bias is going to help adjust for the center or the subtraction, the distance between the origin of the center of the system and the center of the cluster. It is a cluster offset. It is a group offset between the two systems. It is an adjustable parameter, which is kind of interesting because depending on how you do the training, each individual neuron can have its own bias. Technically, it makes a lot of sense that each neuron should have its own bias. Occasionally, you'll see it in the notation that there is one bias for the whole layer. That doesn't make a lot of sense, and I don't think that it always works in most cases. There are some systems that do it that way, but that's kind of messy, all right? So let's treat it, and most of the systems we're working in, PyTorch, TensorFlow, and MATLAB, are going to allow flexibility for the model such that every neuron or every activation relative to the summation of the neuron summation, right? This is the soma of the neuron, is going to have a slight bias. The bias is effectively setting where the activation point is for that neuron. Remember previously I talked to you about the idea that neurons could be kind of predisposed to firing, they could be slightly sensitive, okay? So the sensitivity of the neuron, a higher bias might make the neuron more sensitive, right? More likely to fire under a circumstance. So the bias could be said as a type of polarization or depolarization of the neuron relative to the biological model. Z becomes, once again, this is the circle. Z is the output of that model. Sigma, right, becomes the activation function. And I can place any value or any type of operation, linearity or non-linearity, within the space of the activation function. Linearities aren't super great for activation functions. They typically have some problems. The most primitive system that we have is that step function, right? The simple step, or thresholding activation. And then the next version we have is going to be one that's going to utilize that sigma operation. Connectivity between elements of a neural network follow as such. The input layer. Notice, the entirety of the model that I just described to you exists within every single one of those little circles, right? Every single one of those is a node that takes its inputs and transitions those inputs. So each one of the layers on the input level, right, as we said, we don't care where they come from, but treating it as an input vector or treating it as the output vector of a previous layer, it doesn't matter, okay? It's just whatever the next layer in the system is, its relevant inputs are the effective output of some previous layer. We say that the process of collecting data, encoding it, right, typing it in, measuring it, and typing it in. Processing that data processing system is a process that we call feature extraction. I could say that there is a neural network type process that's involved in that feature extraction, okay? So that first layer, that first set of parameters, the first set of measurements we have is treated as the activations of some previous state, right? The degree to which it's activated is the value that is placed upon each one of these nodes at X. Similar to the slide that I showed earlier, we could call this alpha, right, or A. It doesn't matter. What are the inputs here? The inputs are X. Inputs are the value of X. Notice one thing that's interesting about it. Each of those neurons has its own independent attachment to each of the elements of the feature vector. This is what's called a fully connected network. So, between each of these lines, between each of those little vectors, drawing a line in between the input value and the node of the neuron, right, its function, is a weight. Each of those lines would be represented by a multiplication, right? The degree of which that feature is significant to that neuron is the degree to which that neuron is designed to find that specific pattern of values within the original data vector. Each of the layer elements within the hidden layer is trying to find its own pattern. It's trying to find its own version of something unique or descriptive between the elements. Remember before I said each of these is effectively a linear relationship. I'm going to show you guys something. Hop on to I'll put you guys up a link for this. Some of you have already seen this before, but I think visualizations probably make the most difference or have the most help here. This is called TensorFlow Playground. Okay? And who of you have seen it? Okay, all of my people that were in my classes have seen this because I made them do something on it. Okay? TensorFlow Playground is has the same operability as the TensorFlow Suite package, but it is a web utility. But it only has a finite number of possible data sets to work with. So let's look at the types of data sets we have. Right now we start off with a circle, right? With a circle inside of it. So we have some data points that make up this little center cluster of some feature x1, some feature x2, right? And then we have a group around the outside of it. How easy is this to separate with a single line? Not really, right? But this one would be. This one would be. Okay? I'm going to strip this back real quick. We do not need 2 hidden layers to manage this. We do not need 4 neurons to manage this. Wait, what? All of a sudden it's already there. It's done. It tripped on it. All right? It literally tripped on it. It already had randomly assigned a value that was so close to the actual slope of the separation that it basically fell over and hit it. Now, that's kind of weird, right? That's cool. So let's reset it. Okay, notice what does that look like? That one didn't start off randomized to the right angle. What am I looking at though? I'm looking at a slope, aren't I? Let me run this down here. I'm going to hit the discretize button. If I treat it as a fully discretized linear relationship, and I'm attempting to use a regression to create a decision surface to separate these 2 clusters, what's my goal going to be? My goal is going to be to minimize the error of placement of any given element inside the wrong class. Currently, what is the level of error? Every orange sample, right? Because every orange sample is now considered blue. So I'm going to start the process of adjusting, all right? I'm going to take a single step forward. What happened to the activation? It adjusted it. Now it's actually got some degree of correction, right? Now it actually has some degree of capture that the appropriate elements in the appropriate class. How did it do that? We'll talk about that. That is a process of utilizing back propagation to take the error or the associated error and determine the change in slope based upon the gradient, which is the instantaneous change that indicates the greatest degree of increase in error, right? So negative gradient moves in the opposite direction of the greatest increase in error. That's it. Sounds simple, it's not. It looks really awful in math, okay? But we'll do it. But I want you guys to see what this actually looks like whenever we're dealing with this as a visual system, right? Everybody goes, wow, something really complex. Now it's easy, right? It's easy. You don't have to think more about it. What is happening with the weights? Okay, notice the weight currently 0.38 positive from the feature in x1 and 0.16 negative from the feature in x2. Okay, effectively each one of those is a slope indicating the degree to which the relative significance of the change in the likelihood of being a member of class blue versus class orange is relative to x1, x2 with respect to the feature dimensions of this two-dimensional graph of data. Technically, there are 3 dimensions here. I reiterate this because I want to make this clear. There are 2 feature vectors within this graph, x1 and x2, okay? The third one is what? The class labels. Class label. I have a class label. You can effectively look at it as height, right? How high up on the graph. So the warmer the color you say, the higher the graph is. So if I took this and I turned it down, right, the orange elements would be higher up than the blue elements. The blue elements would be at the bottom and the orange elements up at the top, okay? So there is a surface that I'm going to attempt to describe where I'm going to create a surface that divides those 2 groups together in that 2-dimensional surface. A 2-dimensional surface needs a 2-dimensional discriminant, right? Well, we're going to flatten it to a line because we're looking at it from the edge. So we're looking at it from the edge currently, which means we only need 1 layer of activation in order to be able to output a reasonable discriminant boundary between these 2 classes. So this is the activation of the line system. What I've done is I've started off with the first process of backpropagation. I'm going to take the second step and notice what's happening. It's better, okay? Better. We see the curvature of this particular output here. Notice, test loss, train loss, right? Training loss is slightly lower than testing loss, but they've maintained relative coherence to one another. That means we're doing good. If I keep clicking through this process, notice what's happening to the weights. 0.63 and 0.16, they both become positive. Originally, the slope was negative on the other input, but notice the weight of this original system, 0.63, and the weight of this system, 0.16. This is the input layer, right? But it is already inputting sorted features. Notice it's only inputting features relative to the horizontal axis or relative to the vertical axis, position. The activation relative to those elements is the weight, and then the combination of those activations is a new line, right, that takes into consideration some aspects of the vertical, some aspects of the horizontal. Right now it's taking 63% of the vertical line and 16% of the horizontal line in order to determine the total mass requirement, right, in order to create a balanced separation between these 2 class clusters. I keep going forward in the system. Notice what's happened to the loss. I was getting really good improvement for a while, right? It was really going down. That means if loss is going down, then what happened, right? Gain's going up effectively. So when loss is going down, everything's getting good. What happens when loss levels out? We quit learning, effectively, right? If the loss has completely leveled, that means there's nothing new to learn. I can't make any additional adjustments that will provide any improvement in total performance of the system. I'm going to click forward a few times and let's see if we can get it to go all the way to 0. Okay, notice it's still dropping, but slower and slower every time. Okay, 0.4, 0.3. All right, we're up to 50 different epochs. What do I mean by an epoch? That's each time I stop and check my work, right? I stop, I say I make an adjustment, stop, go back, run everything again, calculate the amount of error, and then make some adjustments, right? Stop, calculate adjustments again. It's a cyclic process. The values have adjusted to where we note here something. The weight of this output is 1.7. What does that mean? That's just the degree to which the adjustment of the activation of that neuron is being calculated or output to the soft max operation, right? And I have another activation operation that's describing or showing this graph. Have I gone to 0 for testing loss yet? Not quite, okay? My training loss is still 0.2. Just gonna run it for a minute, 0.1. Okay, went to 0. Awesome, I have a perfect network. How many people are uncomfortable with this? Okay, let me explain to you something. You wouldn't use a neural network for this. Why? If it's perfectly linearly separable, just establish a threshold. Okay? It doesn't need something as complex as a neural network in order to be able to generate a reasonable output. But I know that I'm not going to be able to do the same thing with this. Right? Or at least I assume I shouldn't be able to. Because no matter how it changes, the slope of that line is still going to be capturing a certain amount of the orange samples in the blue and a certain amount of the blue in the orange. What is it doing now? That's really weird. A line is still capturing some of the data, right? But is it enough? No. So what do?
Increase the degree.
What do? What do I do here? Do you have any ideas? How do I fix this?
Make it curve.
Make it curve. Okay, I like that.
Add more features.
Add more features? All right, let's try that. What do you want to add? X1, X2, sin X. They didn't fix the problem. Not exactly. Okay? Not those features didn't. Could we do it with other features? Maybe, yes. Okay? Features allow us to be able to reframe the problem entirely. I could utilize a radial basis function to turn this into a linearly separable problem. Sure. Okay? So if I use the right pre-processing methodology, I can reproject this set of data. You remember beforehand when I was talking about the idea that if orange was up and blue was down, right? What happens in three-dimensional space? If I turn it like this, it means orange is over here and blue is over here, right? Separable, right? Reprojected in the right way, and the data separable, right? But what am I using? I'm using my knowledge of the class labels, meaning that my model is going to be incredibly biased and is not going to perform well or generalize in the future, right? Possibly, and it's going to make it very difficult. What's one of the other things that I can do to this system? I can add a bunch of noise to it, okay? What's the likelihood that the samples are all going to be 100% clustered within totally blue in the center, totally orange on the outside? Not likely, right? But I will say this. Let's start off 50-50 testing ratio. Let's get rid of the features that we were working with beforehand. Go down just to the set we were working with beforehand so we don't disable ourselves. What if I said I'm going to add 2 additional neurons? Boop.
Wow.
What? What? What has happened though? What's in the middle?
It's 3 lines.
It's 3 lines, it's a triangle. I told you it's just lines. Okay? You didn't believe me. You did not believe me, did you? Okay? So what happens if I want to make it smoother?
Add
Diane,
more
what happens if I
line.
want to make it smoother?
So add more neurons.
Yeah, add more neurons, yeah. Still becomes circle. Oh my god, it's closer.
It's a circle!
Almost.
Yeah.
Almost. It's not there yet.
Almost. We need more.
We need more.
We need more? Okay, well, let's not add more right now. That's a little much. All right, let's increase the batch size a little bit, and let's increase the training ratio. And it should circle.
There you go.
There you go.
Is that a circle?
It's more like a pentagon.
It's a pentagon. Why is it a pentagon?
5.
Because it's made of lines. Okay? I know it's stupid, right? How do I make it smoother? Can I make it smoother?
Oh my
Uh,
god. Boy.
Oh,
Oh, it's
yeah.
almost there. I think it's there. I think it's solid.
How did I make it smoother? By adding 3 neurons in a second layer. 3 parameters. Okay? The elements that are being received at that subsequent hidden layer in the second segment are reconditioning the slopes of the interfaces at the previous layer. They're recombining the features of those elements. Okay? We're gonna figure out what the math is underneath of this, all right? This is the microwave. I teach you how to push the buttons on the microwave, cook your burrito, all right? Later, we're gonna tear the microwave apart so you know how to fix it in case it doesn't work and do what you want it to, okay? We're gonna figure out how to make the microwave work. All right, thank you guys. I'll see you next week. I will put up something for you guys to look through. I want you to review the syllabus, make sure everything is totally up to speed there, and we'll start back again on Tuesday. Have a good weekend.